After too many months of silence, idle concepts rises from the dead. It feels good to be alive again. Hello, this is the density altitude chart featured in the Private Pilot Written test, and in this presentation we will focus on 3 practice questions referring to this specific figure. As I always do, it is recommended to access your own copy of this chart to work along with in the following questions. A free PDF copy will always be accessible at FAA.gov, and a link will be included in the video description below. Now let's go already. To begin, the first question reads, what is the effect of a temperature increase from 35 to 50 degrees Fahrenheit on the density altitude if the pressure altitude remains at 3,000 feet MSL? And we are provided with 3 answer options, with only one of them being correct. Now let's take a look at the figure and see what we are working with here. It is displayed with a graph area on the left side and a conversion table on the right side. This conversion table is useful in situations when you need to find pressure altitude, and to do that with this table, you will need to have an altimeter setting and a given height, which these questions may describe as airport elevation or indicated altitude. As long as you have both of these pieces of information, you will be able to calculate for pressure altitude using this table. The graph side of this figure is helpful when you need to find density altitude, and to accomplish that with this graph, you will need to have temperature and pressure altitude. As long as you have these 2 pieces of information, you will be able to find density altitude using this side of the figure. Now, referring back to our question, it has already provided us with a pressure altitude setting for both temperature scenarios. So that means we have no need to work with a conversion table for this figure, at least for this question. Instead, it is asking about density altitude, so we will need to focus only on the graph side. Let's take a closer look at this graph. We have these diagonal black lines angled upwards from left to right. These lines represent pressure altitude in feet. This red line represents the standard temperature condition. Along the bottom of this graph, we have a temperature scale, including both in degrees Celsius and Fahrenheit. And the last important part is along the left side of this graph is where we will get our density altitude readings. Basically, when using this graph to find density altitude, we will travel in a general path that begins somewhere down at the bottom at the temperature, travel vertically upwards until a certain point for pressure altitude, and then from there, travel horizontally across towards the left side, and at that point, we will see a result for the density altitude reading. So we will follow this pattern with our given question. We will have to compare density altitude with 2 different temperature conditions, the first one being 35 degrees and the second one being 50 degrees, both in Fahrenheit. Taking the temperature information, we will begin this process down at the temperature scale on the graph. Be careful that you're using the appropriate temperature scale, whether it's Fahrenheit or Celsius, because as you can imagine, selecting the wrong one can give you ridiculous results. Locate 35 degrees on the Fahrenheit scale down at the bottom, and then from that point we will travel vertically upwards until we intersect the appropriate diagonal pressure altitude line. In this case, we were given a pressure altitude of 3,000 feet, so that will lead us up to this point on the graph. And then from there, we will travel horizontally across to the left to see where we end up on the density altitude scale. For this given condition, it looks like I got about something just short of 2,000 feet in density altitude. Each of these tiny thin blue lines on the graph represents a 100-foot increment. So for my results, I would estimate that this would look like 1,900 feet. That completes the first part of solving this question. So all we have to do next is to do the same process for the 50-degree temperature condition to compare it with. So we will start at the bottom of this graph again, locate the 50-degree point on the Fahrenheit scale, travel up from there to reach the 3,000-foot pressure altitude line, and from there, travel horizontally straight across to the left side and get our density altitude reading. This time, my results look to be a little short of 3,000 feet. So about 2,900 feet would be my density altitude reading for this condition. At this point, we finished everything we need to do with this chart, and all that is left to do for this question is to compare our two density altitude readings for each given temperature condition. Going from 35 degrees to 50 degrees had us increase from 1,900 to 2,900 feet in density altitude. This gives us a 1,000 foot increase. In that case, we will select answer A as the correct answer. A quick tip to remember here is that when it comes to density altitude, any increase in temperature results in an increase in density altitude as well, and vice versa. A decrease in temperature will result in a decrease in density altitude. This applies when pressure altitude remains constant, as it did in this question. Understanding the relationship between temperature and density altitude, you can apply the process of elimination with the following answer options here. This question is asking with a given constant pressure altitude and a temperature increasing from 35 to 50 degrees. With these conditions, you can simply eliminate answer option B since it says a decrease. That would leave us with a bigger gap between the remaining answer options, having to select between 1,000 feet or 1,300 feet, increasing. This makes it easier to select the best and closest answer if our results were a bit difficult to read, especially when hand drawing on this graph. So in this case, it looked quite clear that we experienced almost exactly a 1,000 foot increase. So this was a simple one to solve. But in case for future questions, the best answer may not always be as obvious, especially if our hand-drawn lines are a bit crooked or were drawn thicker. As you can recall, each of those tightly spaced thin blue lines on the graph represent 100 feet, so it doesn't take much to lose precision here. Take the time and effort when drawing your lines on any kind of these performance graphs. Let's move on now. What is the effect of a temperature decrease and a pressure altitude increase on the density altitude from 90 degrees Fahrenheit and 1,250 foot pressure altitude to 55 degrees Fahrenheit and 1,750 foot pressure altitude? Goodness, sometimes reading this stuff out loud is still so difficult for me. So in this case, since we are working with the changes in pressure altitude, we cannot simply apply the process of elimination as we did in the previous question. However, to solve this question, it's not that much more complicated. In this scenario, we will simply compare the density altitudes for each of these given conditions. Let's begin by solving for the first condition. As we have done before, we will start at the bottom of the chart on the temperature scale and locate 90 degrees Fahrenheit. Travel up from there to reach 1,250 feet in pressure altitude. Now, this is where we don't have an actual line drawn for this given pressure altitude specifically, so we will have to estimate where in between the 1,000 and 2,000 foot lines would be our 1,250 foot pressure altitude. And when doing that, remember that these lines are slanted, so we will have to track upwards parallel to them. Each of these thin blue lines represent 100-foot increments, so in aligning with them as much as possible, I attempt to find the spot. What I ended up doing here is to start by drawing the midway point between 1,000 and 2,000 feet. That line would be my 1,500-foot line. And since 1,250 feet is halfway between 1,500 and 1,000 feet, I drew a line halfway between there to find my spot on the graph to find the pressure altitude. After finding my spot for the pressure altitude, I will travel straight across from there to the left and read my density altitude. Well, it looks like for this given set of conditions, the density altitude reads at about 3,500 feet. Now we will do the same process for the second set of given conditions in the questions. We have 55 degrees Fahrenheit and a pressure altitude of 1,750 feet. Let's go to the bottom of the graph and select 55 degrees on the Fahrenheit scale and travel up from there to reach it looks like we have to do the same thing where we have to estimate where the 1,750 foot line would be drawn on this graph. So I will use the same method as we used in the previous set of conditions. Again, I estimated where the midway point would be between the 1,000 and 2,000 foot pressure altitude line would be, and then halfway in between the 1,500 and 2,000 foot line would be our targeted 1,750 foot pressure altitude line. And then, from there, travel straight across to the left, and taking a closer look at where we ended up on the density altitude scale, it looks like we ended up with around 1,700 feet. Getting close to the end here, we will take this density altitude reading and compare it with the density altitude from the first set of given conditions, which was 3,500. Subtracting 1,700 from 3,500 shows that we have a difference of 1,800 feet in the decreasing direction. So finally, with the given answer options, option C, 1,700 foot decrease, would be the best or closest answer for our scenario. If we were to go back and attempt to solve for this question multiple times, it would not be unusual to get slightly varying results each time, since we are manually hand drawing and estimating our tracks along the graph. The important thing to do in these kinds of questions is that you take your time to draw your lines as accurately as possible and having to choose the best answer out of the given options we have to work with, and move on with your life from there. Now let's change the routine a little bit and practice using this conversion table included with the figure. As we can see, this table lists altimeter settings and their corresponding conversion factors to get pressure altitude, simply based on the given altimeter setting and height. All there is to do with this table is, if we know our altimeter setting, we would refer to the right-hand column to either add or subtract the matching conversion factor number to our given height. Doing this will provide us with a pressure altitude. Remember, we cannot calculate for density altitude if we do not have both temperature and pressure altitude information. So let's practice how to calculate for pressure altitude with some examples. How about if our given elevation at an airport would be 2,000 feet and our altimeter setting was 28.9? This would lead us to a conversion factor of 957. This means that we would need to add 957 to our elevation of 2,000 feet, and our pressure altitude would be 2,957. Note that these negative conversion factors that begin to appear towards the bottom half of this table simply means that we would need to subtract these quantities from our elevation or height. Now let's apply that to some more sample questions to practice and review how this all works together. How about determine the density altitude for these conditions: altimeter setting 29.25, runway temperature 81 degrees Fahrenheit, and airport elevation is 5,250 feet above mean sea level. As always, we are given 3 answer options to select from. And don't be surprised if these written test questions give an altimeter setting that is not directly listed on the table. As in this case, 29.25 is not listed in this table, and we only have 29.2 and 29.3. We would know that 29.25 would be somewhere in between these two settings. So what is commonly done in these kinds of situations is that we would need to take the average between the provided conversion factors of 29.2 and 29.3, which would be 673 and 579. To do that, we would add these two numbers up and divide it by 2, and we would get the average conversion factor of 626 feet. We will then add this number to our given airport elevation of 5,250 feet, which that would result in 5,876 foot pressure altitude. If the question was asking for pressure altitude, we would already be done at this point. But since, looking back at the question, it is asking for density altitude, indicating that we are not quite done yet. So we will take that pressure altitude that we figured out and apply that to our process of figuring out density altitude using the graph side of this figure. So as we have practiced before on this graph, we will begin down at the given temperature scale and find 81 degrees Fahrenheit, track up from there, and reach up to the point where our pressure altitude would be. And in this case, we got 5,876. That would have been estimated as best as possible on this graph up here. I'm hoping that I'm close enough. And then from there, we would go straight across to the left and read what our density altitude would be. To me, the density altitude here appears to be pretty close to 8,000 feet. So from here, let's take a look once more at the answer options we have to work with. It doesn't take long to see that answer option C is the closest to our density altitude reading of about 8,000 feet. So in this case, I would go with option C, 8,500 feet MSL, which is also identified as the correct answer in these written tests. Also, take a look at the listed answer options here. Remember how in the earlier stages of solving for this question, we figured out that pressure altitude was about 5,876 feet. It looks like answer option B here could have played to be a tempting trap into selecting the wrong answer for this question if we stopped too early in the solving process. Pressure altitude is not the same as density altitude. So to wrap up this video, I just want to leave you with the idea that, as we saw, using these charts and tables are really quite simple, almost boring. There is nothing much more complicated to them beyond just adding or subtracting and drawing an L-shaped line on this graph. But human error is something that each of us can fall to at some point, and don't let this simplicity lure us into complacency and make silly mistakes during the test. Take time and double-check your work, draw thin and straight lines on these graph charts, and go ace your written test. See you later!